Good evening, everyone. My name is XIANG Li. My ZID is z5604082. This is my student ID card. Today, I'm gonna talk about my final video for the gravity and orbits experiment in Physics 1160. In this presentation, I will explain Kepler's 3 laws, question 9, question 11, and my result for question 13 to 16. First, Kepler's 3 laws. Kepler's first law states that planets orbit the Sun in ellipse with the Sun at one focus. In other words, orbits are not perfect circulars. They can be stretched depending on the speed and distance. Kepler's second law says that a line from a planet to the Sun sweeps out equal area in equal times. This means planets move faster when they are closer to the Sun and slower when they are farther away. Kepler's third law tells us that the square of the orbital period is proportional to the cube of the orbital distance, so larger orbits naturally have much longer periods. For question 9, in the planet moon systems, the planet does move. Both the planets and the moon orbit their shared center of mass, called barycenter. Because the planet is more massive, the barycenter sits close to the planet, so its motion is small but still noticeable. In some planet systems, the Sun is so massive that the barycenter lies inside the Sun, so the Sun barely moves while the planet completely almost the entire orbit. The difference is that the planet moon barycenter is outside the planet, where the Sun planet barycenter is deep inside the Sun. For question 11, when I turn on the grid line in the 2-square mode, the default distance between the star and the planet is 1 AU. This distance spans 2 grid squares, so 1 grid square equal to 0.5 AU. For question 13 and 14, I create 4 nearly circular orbits by adjusting the lines of the velocity arrow. At 0.5 AU, I increase the velocity. At 1 AU, the default Earth orbit was already circular. At 1.5 AU, I slightly reduced the velocity. Finally, at 2 AU, I reduced the velocity even more. After small adjustment, all 4 distances produce stable, nearly circular orbits. Here are the orbital period I measured. For 0.5 AU, it takes 121 Earth days. For 1 AU, it takes 365 Earth days. And for 1.5 AU, it takes 500 Earth days. And the last one, for 2 AU, it takes 715 Earth days. As distance increases, the orbital period increases significantly. These results follow Kepler's third law. Even though the simulation is not perfect physical, the trig mesh p square is proportional to a cube. It means large radius and longer period, and the ratio of p square and a cube increase together. For question 15, the planets at 0.5 AU move the fastest, and the planet at 2 AU move the slowest. This happens because the closer a planet is to the star, the stronger the gravitational pull it feels, and therefore the higher the speed it needs to maintain a stable circular orbit. On the other hand, planets that are further away experience weaker gravity and move more slowly. So the difference in speed is simply a result of how gravity changes with the distance. From this activity, I learned how orbital distance control both orbital speed and orbital period. By manually adjusting velocity, I solve how circular and elliptical orbit form based on the balance between gravity and tangential motion. I also solve how Kepler's laws appear naturally. Inner orbits are fast, outer orbits are slow, and the orbital period increases strongly with distance. This helped me understand why planetary systems have the structure they do. Thank you for watching my video. This includes my final presentation for gravity and orbits experiment. Bye.